Well, for the last couple days, you've had some experience working with the second derivative and seeing how that was so useful for determining concavity and finding points of inflection. One other use of the second derivative can actually go back and help us verify maxes and mins. So we're going to see how that is useful in something called the second derivative test today. So just think back about every max and min. So we know that maxes and mins are identified by horizontal tangents. So all of them, all of these at least, have horizontal tangents. And so do all of the mins have horizontal tangents. So just knowing that a function has a horizontal tangent can't help us decide if that horizontal tangent belongs to a max or if the horizontal tangent belongs to a min. But if we look also at the second derivative, we can tell the concavity. So we could tell that every max sits on top of a section that is negative concavity. Every single max has that common feature. Not only do they have a horizontal tangent, but they sit on top of a negative concavity. On the flip side, all of the minimums sit at the bottom of a section that has positive concavity. So positive concavity is indicative of a minimum being below it. And so we can use the horizontal tangent, which isn't enough to tell us if it's a max or a min, but we could use the horizontal tangent with the concavity, and that would be enough to prove the existence of a max or a min. So that leads us to the second derivative test. So the second derivative test says if f prime of c equals 0. That means if you have a horizontal tangent. So if we have a horizontal tangent. Now this does not work for cusps, doesn't work for corners. It only works for horizontal tangents. So if we have a horizontal tangent and if the second derivative is less than 0, so that means concave down, then we have a maximum. So sometimes I encourage students to draw it. Draw a horizontal tangent and draw concave down. It should be clear that that is a maximum point sitting at the top of the vertex there. So the flip side is if you have a horizontal tangent, f prime equals 0, and if f double prime is concave up, then we have a local minimum. So again, I say draw it. Draw a horizontal tangent and draw something that is concave up attached to that. That is a minimum value right there. So having a horizontal tangent by itself is not enough. Having a horizontal tangent with a change in the first derivative from a plus to a minus or a minus to a plus, that would be enough. Or having a horizontal tangent and either concave down or concave up, that would be enough. So horizontal tangents by themselves do not prove maxes or mins, but horizontal tangents and plus minus or minus plus changes in the first derivative, or concave up, concave down, that is enough. So let's use the second derivative test here. Find the local extreme values, and we're going to do the second derivative today. So to do extreme values, we need the first and the second. The first is going to be 3x squared minus 6. The second will be 6x. We take the first and we set it equal to 0, and we solve. Sorry, set it equal to 0. We solve that, which will tell me that x is equal to add 6, divide by 3, and use a plus or minus square root. So x is equal to the plus or minus square root of 2. That tells me that I have horizontal tangents at those two places. That is not enough to tell me if those horizontal tangents are going to be extreme maxes or extreme mins. But I can use the second derivative to check it out. So f prime of rad 2, okay, remember f prime, the original one, that's equal to 0. That's the horizontal tangent. And, there's always an and, we want to check something else in addition to the horizontal tangent. F double prime of rad 2 would be 6 rad 2, which is greater than 0, which means we've got a horizontal tangent and we have concave up. So what does that mean? A horizontal tangent with concave up. That means that x equals rad 2 is a min. That's enough to have the horizontal tangent and concave up. So let's check the other one. F single prime of negative rad 2. We know that's also equal to 0. But we need the and. We need something else. So we have a horizontal tangent for sure. And let's see what f double prime. F double prime of negative rad 2. That would be 6 times negative rad 2, or negative 6 rad 2. That's less than 0. So that means I have concave down. So that would be a horizontal tangent and concave down. That means that x equals negative rad 2 is a max. So I can't hit that hard enough that a horizontal tangent by itself is never enough to prove an extreme max or min. Those extreme values can't be proved by one thing. They have to be proved by a horizontal tangent. And I could go back to the first derivative test, which means making a plus minus chart and checking that. That would be enough. Or I can check the second derivative, and that would be enough. Either one or the other. We're going to practice the second derivative today. All right, find the local extreme values for 2e to the negative x squared. So we're going to need a y prime, and we're going to need a y double prime. Y prime is going to give me the 3-part derivative, 2e to the negative x squared times the natural log of e times negative 2x. We're going to set that equal to 0. Of course, Lenny is never equal to 0. Negative 2x squared is never equal to 0 either, because it's an exponential, and exponentials never touch the x-axis. So the only thing that might be equal to 0 is negative 2x, so that tells us the only possible candidate is x equals 0. Now that's enough to tell me I have a horizontal tangent, but it is not enough to tell me if I'm an extreme max or extreme min. So now I need the second derivative. Kind of wish I hadn't crossed out some of that stuff because I'm going to need it for my second derivative. My second derivative is going to need the product rule. So I'm going to be working on this part and this part, since Lenny is 1 and not part of it. So we'll use our product rule. Negative 2x times 2e to the negative x squared times Lenny times negative 2x plus second part of the product rule. So 2e to the negative x squared times negative 2. So we can clean this up significantly. So we've got positive 8x, e to the negative x squared minus 4 e to the negative x squared, which really is 8x over e to the x squared minus 4 over e to the x squared. Now we know we have enough to have a horizontal tangent, but we want to know what kind of horizontal tangent is it? Is it the horizontal tangent that has negative concavity, or is it the horizontal tangent that has positive concavity? So we want to check the second derivative. So we're going to check what y double prime of our value 0 happens to be. So we'll plug in 0 for the second derivative. So 8 times 0 over e to the 0 squared, and then minus 4 over e to the 0 squared. So 8 times 0, of course, is 0. Minus 4 over e to the 0 squared is 1, so it's negative 4. So that is a negative number. That means we have concave down, which means our winner is this one right here. Horizontal tangent with concave down, which tells me that x equals 0 is a local extreme max. Because there was a horizontal tangent and there was concave down. So those two reasons are enough for me to say that I have a local extreme max. Now here's a little bit different way of asking a similar question. Does q of x, which is equal to f of 2x, have a critical point at x is 2? It's another way of saying, does it have an extreme value at x is 2? So first, we have to check if it has a horizontal tangent at x is 2. So we're going to be checking what is q prime. And then once we've established that, we'll be checking what is q double prime. So q prime of f of 2x means I apply the chain rule. So I'll be working on the outside multiplied by the derivative of the inside. So f prime on the outside of 2x times 2. When I want the, which is the second derivative, I'll be using the product rule. So I'll have 2 times f double prime of 2x times a chain rule of 2 plus f prime of 2x and then the product rule of 0. So since I have the product rule of 0, we can get rid of that whole back section. All right, now I'm ready to evaluate when x is 2. So I want to be looking at, all right, let's figure out what q prime at 2 is. So if q prime of x is f prime of 2x times 2, then q prime of 2 would be f prime of 4 times 2. And according to the chart, f prime at 4, okay, so here's 4, and there's the f prime value, so that's going to be equal to 0. And again, what does a prime value of 0 tell you? It tells you that you have a horizontal tangent. It does not tell you if you have a critical point. You need to know what q double prime at 2 is. So q double prime at 2 is going to be, well, I've got 2 and then a chain rule, so I'll have 4 times f double prime at 4. So going back to the chart again, since we've got at 4 f double prime of 4 is -3, so that'll be 4 times -3, which means -12. And what that tells me is that I am concave down. So if we can picture that, we've got a horizontal tangent combined with concave down, which means that the critical point we're looking at is a max. So q of x has a local max at x equals 2. All right, to wrap everything up now, okay, so we're going to put everything together from this whole week. We want to go back to how do we read a graph, okay, what are we learning from a graph when the graph is the derivative and not the original graph. All right, it would be very easy for me to say, look at this graph and find the minimums if it was just a regular graph, but it's not. This is a derivative graph. So we need to hone in on what are we looking for a derivative graph. All right, here are we going to look for specifically. This graph is representing the derivative. We want to find local maximum values. Maximum means f prime of x equals 0 and something else. All right, so and ... Local maximums mean f prime equals 0. Well, f prime is the graph. And so f prime is equal to 0 3 times. 1, 2, 3. So when we are looking at that, those are the 3 possibilities for local maximums. The and is not only does the prime have to be equal to 0, and the prime must change. F prime of x changes, and if it's going to be a maximum, it's changing from plus to minus. And the only place that this function is changing from plus to minus is right here. And so the only maximum value is happening at x equals, what is that, -2. Now we want a local minimum value. The local minimum value, the definition of that is when f prime of x equals 0 and ... And the and is that f prime changes from minus to plus. Because that means the slope is changing from decreasing to increasing. And the only place that is happening right here at positive 2. And so x would be equal to positive 2 for the minimum value. What does that mean about the origin? Nothing. It means it's not a maximum or a minimum. It's neither at the moment. All right, I'll also find the interval in which the function is rising. Go back to the definition. Rising means f derivative is above the x-axis. And so where do we see that? Well, we see it in quadrant 2 and we see it in quadrant 1. That is where the derivative is above the x-axis. So we see it's rising when x is less than negative 2, and we see it rising when x is greater than positive 2. And then finally, when would it be falling or decreasing? Well, the definition of falling is when the first derivative is below the x-axis or less than 0. And we see the first derivative being below the x-axis in quadrant 3 and again in quadrant 4. And so we would say that it is falling when, let me see if I can fit this in here, x is between negative 2 and 0 and between 0 and 2. So those are the definitions of when we would have maximums and minimums based on the definitions from a derivative graph. And we've done that before. We've done that with velocity. We've done that earlier this week. But now we can do it with points of inflection. Find the x-coordinate where the graph would have, the original graph would have a point of inflection based on only looking at the derivative graph. And so our point of inflection, the definition of point of inflection, always go back to what the definition is. The definition is when f double prime of x is changing. Now f double prime of x is the slope of f single prime of x. So anytime the slope changes direction, we're going to have a point of inflection. Anytime the slope changes direction. So the slope changes direction 3 times. Changes direction from decreasing to increasing, from increasing back to decreasing, and from decreasing back to increasing again. So the points of inflection are now, that's what that origin means. That origin is one of those points of inflection. So our points of inflection are x equals, that's approximately negative 1.5, we're going to estimate. And it's happening at 0, and it's happening at positive 1.5. Those are the 3 points of inflection because those are the 3 direction changes for the derivative graph. And we can find the intervals on which f of x is concave up when we go to the definition of what it means to be concave up. And the definition of concave up is when f double prime is positive, aka, okay, so in other words, are also known as the slope of f of x, f prime of x, is positive. So the slope is positive 2 different times. The slope is positive between negative 1.5 and 0. And the slope is positive again. Now, I'm not talking about it's crossing the x-axis. I'm just talking about positive slope, where the graph is going in a positive direction, an increasing direction. And so we are concave up from negative 1.5 up to 0. And we're positive again from x being greater than 1.5. So then we know our graph is concave down. The original graph will be concave down when what we're looking at, which is the derivative graph, has negative slope or is decreasing. So our decreasing intervals are there, which means the original graph is concave down. It doesn't mean this graph is concave down. This is a graph that is not the original graph. This is a derivative graph. And so let me see. We want to say it's concave down when f double prime is negative, which means the slope of the derivative graph is negative, which then takes us to x being less than negative 1.5 and x being between 0 and 1.5. Okay, trust your definitions. Don't trust what your eyes see. Your eyes are going to play tricks on you. Always go back to what's the definition of the thing I'm looking for, and how does that fit in with the graph I've been given. All right, we're going to try that one last time. This one is a discontinuous graph, but the definitions still hold. Okay, the definitions still hold. All right, let's find the x-coordinates where we have a local max. And remember that the definition of a local max and a local min starts with f prime of x being equal to 0. So we start with that. We start with f prime of x being equal to 0. Well, that happens here at A and at C and at E and at G. But the definition of a max can also include when the derivative is undefined. It can include points of discontinuity. Those can also be maxes or mins. So it can also be F. So we've got A, C, E, and F. So how do we tell if they are maxes or mins? So remember, a maximum is when the graph is changing from positive to negative values. So around C, we're changing from positive to negative values. Around G, we are changing from positive to negative values. We are not changing from positive to negative values around A or E or F. So our maximum values would be at C and at G. Those are the two local maximums. They meet the definition. The definition is that the first derivative is equal to 0 and changing from positive to negative. So what about the other ones? Well, the other ones are changing from negative to positive. So is E, from negative to positive. So that's going to be a local min for both of those. But F is not changing from negative to positive either. Both sides of F are both positive sides. Those arrows on either side are both going up. So what does that mean? Well, nothing yet. Okay, nothing yet. But keep that in mind. F is going to be important. Then we want to know when what the intervals are where the function would be rising. So rising is going to be anything in a positive quadrant. So it will be rising from A to C. It will be rising from E to F and from F to G. Okay, rising on anything that is above the x-axis. And so we can answer our rising intervals as saying from A to C, from E to F, and from F to G. Our falling intervals are anything below the x-axis. So anything less than A is below the x-axis. Anything from C to E is below the x-axis. And anything greater than F is below the x-axis as well. So that'll be our falling or our decreasing section. All right, last. How do we find the inflection points? The inflection point is anywhere that the slope of the derivative graph changes direction. So that is going to be happening at B. It's going to be happening at D. And now it also will be happening at F. We do have a complete change of direction those three spots. So my inflection points can include a point of discontinuity. That's not a problem for an inflection point. So we'll have B, D, and F because the slope or the direction of the derivative graph is changing, which means it will be an inflection point on the original graph. Around those points are going to be all changes in concavity. So up until B, the function is completely increasing. That would be concave up. From D through E all the way to the point of discontinuity, that is also an increasing section. So concave up is going to be anything greater than A. Excuse me, nope. Anything less than B, and anything between D and F. Our concave down sections are anything that slopes down. So that would be B to D, and then from F through G all the way to the end. So those are our concave down sections. So from B to D, and then from anything that is greater than F all the way through G to the end, that's also going to be concave down. So stick with your definitions. Try not to let your eyes play tricks on you. Try to discipline yourselves to be looking for zeros. I'm looking for changes from one quadrant to the next. I'm looking for places where positive values change to negative values, those kinds of things when you're reading graphs. And you'll get better and better and better as we progress throughout this unit and throughout the rest of the semester. All right, I will see you back next week. I hope you have good success with this. If not, I will iron out any wrinkles that are left after the Monday holiday. All right, have a great one.